would be zero. So to make that short, what we're saying is that if a particle is in equilibrium, the virtual work will be zero. The second principle states that a particle is in equilibrium under the action of a system of forces, which includes again the inertial force NA, if the total work done by the forces, the virtual work, is zero for any virtual, imaginary displacement of the particle. So this kind of turns it around and says that if the total work done by the forces, in other words, the virtual work done, if that work done is zero, then we conclude that the particle is in equilibrium. And finally, the third principle states that a particle is in equilibrium under the action of a system of forces, which includes the inertial force NA, so we start exactly the same way. If the total work done by the forces, but in this case we're going to exclude the reaction forces. Like we saw in the previous two examples, there were two reactionary forces, but if we now exclude those forces, the virtual work done will also be zero for any kinematically admissible virtual displacement. In other words, a displacement that is possible that does not violate the constraints. In other words, a particle sliding on a table can somehow go through the table. That would be an example of a particle that violates the constraints. So if a particle does not violate any of the constraints, then, again, also if it's kinematically admissible virtual displacement, then we can exclude the reaction forces, and again, the particle will be in equilibrium if the total work done, virtual work, by the forces equals zero. And those are what we call the three principles of virtual work. Welcome to my lecture online. In this video, we're going to show you how to take the inverse of a complex number, and we're going to do it in polar form. So if this is the general form of the complex number in polar form, then we can represent the number 1, the real number 1, also in polar form. This would be the length of that number, the magnitude, or the modulus, and of course, that means that the angle must be 0, so you have the cosine of 0 plus I times the sine of 0. The sine of 0, of course, is equal to 0, and the cosine of 0 is 1, so 1 equals 1. So that's simply a polar representation of the real number 1. The reason why we did that is now we're going to take the inverse by using the quotient rule, 1 divided by z. And z, of course, is the complex number in polar form, and 1 is also going to be written in polar form, because now we can use the general approach that says that z1 divided by z2 is equal to the ratio of the moduli, r1 and r2, times the cosine of the difference of the two angles, theta 1 minus theta 2, plus I times the, I don't need that parentheses there, times the sine of theta 1 minus theta 2. So we use the exact same approach to see what we end up with. We can go ahead and find the inverse of this. So this becomes equal to 1 over r. R, of course, is the modulus of the complex number times the cosine of theta 1 minus theta 2. Now, theta 1 is the angle on top, so this would be 0 minus theta, and that would then be plus I times the sine of 0 minus theta. Now, we can simplify that, so this becomes equal to 1 over r times. Now here we have 0 minus theta, that's basically minus theta, but the cosine of a negative angle is the same as the cosine of a positive angle. So this can be written as the cosine of theta. But here we have the sine of 0 minus theta, which is the sine of minus theta. Now the sine of a negative angle is equal to the negative sine of the positive angle. So this becomes minus I times the sine of theta. And so the only thing we have to do to take the inverse of a complex number, once it's in polar form, is to take the inverse of the modulus, and then you make this a negative instead of a positive. That's all we have to do. Everything else stays the same. And that's how it's done. Welcome to our lecture online. Let's talk about the different kinds of binary star systems that we can see. Or, in some cases, we don't necessarily see them, but we can detect them in certain ways. Now, not all binary star systems have 2 stars to the system. Sometimes we call stars systems that have 3 or 4 stars. Also, binary star systems, although recently we've gotten kind of away from that, and so now we say there's a system of 3 stars or a system of 4 stars, and typically binary star systems now more recently have been allocated to where we have just 2 stars in the system. The 7 different kinds of binary star systems that you can encounter are called optical binaries, visual binaries, eclipsing binaries, astrometric binaries, spectroscopic binaries, spectrum binaries, and contact binaries. Well, what are these? Well, first of all, the optical binaries are really not really binary star systems. They just appear to be a binary star system because from our vantage point, 2 stars may be very close together. The angle between them may be absolutely minute in the terms of maybe fractions of an arc second. And so they appear to be a binary star system. Sometimes we look out there and say, oh, look, that looks like a binary star system. Then in essence, they're very far apart. They just appear to look like a binary star system. So we call them optical binaries. Now, visual binaries, where we actually do have the binary star system, and as we're taking photographs of them, over time, we can see one of the stars moving around the other star. So we can see that as time goes by, sometimes days, weeks, months, or years, depends upon how far they are apart, what the masses are, and how long it takes the one to go around the other. We can then take pictures and see, indeed, yes, that is a binary star system. We have a visual picture of it, so we call them visual binaries. Sometimes we notice when we look at a star that the star, on occasion, the light of it dims and becomes bright again, dims, becomes bright again, and quite often the dimming is not equal when it happens twice in the orbit of one star around the other. We may not be able to distinguish the existence of the second star in any other way except realizing that when one star moves in front of the other, typically the smaller one, which has a lower surface temperature, and therefore it doesn't give off as much light per unit area, it therefore dims the totality of light we receive from the binary star system, so we have a dimming period. Then when that small star moves behind the other star, instead of being next to it, when the star is next to it, we receive the light of both of the stars. When the small star moves behind the big star, then we have a little bit of dimming because we no longer see the light of the smaller star. We call that eclipsing binary because one star will eclipse the light of the other. The fourth one, asymmetric binary, is where we actually detect the wobble, the movement of one star because of the presence of another one. We may not be able to see the second star, but we do see the wobbling of the first star, and so therefore we say there must be a binary star system because one star appears to be moving or revolving around something else that we can't see, but it must be there, so we call that an asymmetric binary. A spectroscopic binary is where we can actually detect the light shifts, blue shift and the red shift of one star moving around another star. If they're located in such a way that they do not move in front of one another, but we can still see the radio closing and opening velocities, we can measure those velocities and measure the blue shift and the red shift of one star as it goes around the other. We call those spectroscopic binaries. We also have binaries which are called spectrum binaries. The difference there is that we cannot see necessarily the blue shift or the red shift, but what we can see is that we have a spectrum that appears to have the indicators of two very different stars. And so we then separate those, saying, oh, these lines belong to one star, the other lines belong to another star, so we can see that together they appear as one star, but we realize then, because of the specific spectral class, the spectral type they may be in, we see different lines in the spectrum at different intensities, and therefore we can break it out and realize, hey, we have two stars there instead of one star, and we call that the spectrum binary. And finally, we have a type of star called the contact binary, where the two stars that are very close together, where one has gone through a different evolutionary stage than the other. Maybe one is already a white dwarf, and the other one now has become a red giant, so that the outer surface of the red giant becomes very close to the white dwarf, which has a very strong gravitational pull when you get close to it, and so some of the material gets pulled off the big star onto the small star in such a way that they actually appear to make contact, so we call them contact binaries. So those are the 7 main types of binary star systems that we have, and we'll talk more in detail about what they are and what we can learn from them by studying them in various ways. And that's how we know more about binary star systems. Welcome to our lecture online. Work is something we do in nature by applying a force and have that force act over a certain amount of displacement. Now, we did say force and displacement, which implies that these two are vectors. And if the direction of the force is different than the direction of the displacement, and there's an angle between the two, we can then define the work done as being the dot product between the force applied and the displacement. Therefore, it is equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. Notice when the angle between them becomes 0, the cosine of 0 is 1, and it simply becomes the product of the force times the distance. Now, what happens when the force is not a constant, when we're not applying a constant force? Then, of course, for every small displacement, the force will be different, and that, of course, lends itself to using the methodology of integration. So here, let's say that we're applying a force from A to B, that's our displacement, and let's make it a little bit easier and assume that the direction of the force applied and the direction of the displacement is the same, so that the angle between them is 0. Let's assume that we have now applied the force for a while, and now we're in this location right here, and we're applying the force for another small displacement dx. So a small amount of work will be done, let's call it a dw, which is equal to the force at that particular location times the displacement dx. And of course, we'll do that for every small little displacement all the way across, and when we sum all that up, that will be the total work done. Understanding that the force will be a function of position x, in other words, the force will change as we go from A to B in some fashion, according to some sort of function, and we have to define that function. You can then see that the work done will simply be the sum of all those little forces times displacements, or the integral of the function representing the force times the displacement dx all the way from A to B. And that's how we then define the work done using that integral. And that's how it's done. Lecture line. Now let's do an example of how to divide one complex number by another when they are in polar form. Remember, the equation that we found on the previous video was that we divide V1 by V2, that is equal to the ratio of the moduli, which is R1 divided by R2 times the cosine of theta 1 minus theta 2 plus I times the sine of theta 1 minus theta 2. In other words, we subtract the arguments from the first one and we take the quotient of the moduli. So let's go ahead and now plug in what we have, and obviously we've already converted from the normal A plus BI format into the polar format like we did in the previous videos, and now we can just simply plug this in. So this is equal to R1, which is the square root of 2, divided by R2, which is 2, times the cosine of theta 1, which is a minus pi over 4, minus theta 2, which would be pi over 6, plus I times the sine. We're going to get the same arguments here. That would be minus pi over 4, minus pi over 6. Now let's simplify this and see what this then looks like in its final form. The square root of 2 over 2 times. So minus pi over 4, minus pi over 6, common denominator. Again, it's very easy once you have it in the polar form. Welcome to our lecture line. Here we're starting a series of videos on astrophysics. Now, astrophysics is a broad subject and there's many topics. So to give you a feel of what we'll be covering, here we have some of the main content. Now, this does not cover all of the content we're going to talk about, but at least it gives you a pretty good idea. So I'm thinking about perhaps 12 playlists. The first one will talk about binary systems, Kepler's laws, Newton's laws, and mass determination. Then we'll move on to star equilibrium, nuclear fusion, luminosity, and pulsing. Then we have a series on static equilibrium in gases and the Maxwell-Boltzmann distribution of those gases. We have stellar life cycle and stellar structure in section 4. Section 5 will include thermal radiation, luminosity, and intensity. Then we'll talk about the black body radiation curve and the expansion of the universe. Then we'll have a section on relativity in astronomy. Then we have synchrotron radiation, something that's very common in space, radiated power, and particle emissions. Then we'll have a section on constant scattering. Then we have hydrogen radiation and the spin flip radiation, also known as the 21 centimeter radiation. Then we'll have a section on the index of refraction and Faraday rotation, and the last section on gravitational lensing. And again, by no means will that be all that we'll be covering. There'll be more smaller topics included in some of these lists as well. But at least that gives you a good idea of what we're going to talk about. It'll be a lot of fun. I really like astronomy. I like astrophysics because in astrophysics you actually do the calculations and the equations that show you how everything works in the universe. So it'll be a lot of fun. And if you're interested, stay tuned. We will have a lot of videos for you. It take a little while to get them on the playlist because without very busy people, but we're doing our best to put as much as we can in our videos. Welcome to my lecture line. Now let's see if we can come up with an equation that shows us how to divide two complex numbers when they're in polar form. Again, we have the same two complex numbers in general form. Now we're going to divide them. Let's see what that looks like. Now again, when we divide complex numbers, we're going to need to multiply the numerator and the denominator of that fraction by the conjugate of the denominator. This means that we're going to multiply this times the numerator. We're going to get the cosine of theta 2 minus I times the sine of theta 2. And of course, the very same thing in the denominator. You can see, of course, that the modulus of the first one is divided by the modulus of the second one. Just like when we multiply the moduli, here we divide one by the other. But what does the rest of it look like? All right, let's see what that turns out to be. In the numerator, we're going to get R1 times the cosine of this times the cosine of that. So we get the cosine of theta 1 times the cosine of theta 2. This times that gives us minus I times the cosine of theta 1 times the sine of theta 2. Then this times this gives us plus I times the sine of theta 1 times the cosine of theta 2, and then this times this gives us minus I squared times the sine of theta 1 times the sine of theta 2. Alright, that's quite the numerator. Now we divide that by the denominator. We have an R2 times, but now realizing here, that's why we took the conjugate, that the middle term is going to disappear because I have a plus I sine theta 2 and a minus I sine theta 2, which means in the denominator we end up with the cosine of theta 2 times the cosine of theta 2 squared, so that's the cosine squared of that, minus I squared times the sine of the same angle squared. And of course, I squared is negative 1, which makes it positive, which makes the whole denominator become 1. So that means that is equal to the ratio of R1 divided by R2 times what we have left in the numerator. Now, let's see, we're going to combine this, and this goes to the real part, that becomes negative 1 times negative 1. So we have the cosine of theta 1 times the cosine of theta 2, plus the sine of theta 1 times the sine of theta 2, and that looks familiar. That looks like the cosine of theta 1 minus theta 2. And then here we'll factor out a plus I, or maybe we should factor out a minus I. I think minus I would be better. Minus I, and that becomes the cosine of theta 1 times the sine of theta 2, and this becomes then a minus sine of theta 1 times the cosine of theta 2, and that is also looking familiar, because this looks like, let's see here, that's the sine of that minus that would be equal to the sine of theta 1 minus theta 2. Yes, it does. Alright, so now we can finish. So this is equal to R1 divided by R2 times the cosine of theta 1 minus theta 2, and that would be minus I times the sine of theta 1, and I'm talking, I need this parenthesis here, the sine of theta 1 minus theta 2. And actually, let's see here, if we multiply this negative in with this negative, then this switches around to get the sine of theta 1 cosine theta 2 minus cosine theta 1 sine of theta 2, which is equal to the positive of that. So that's going to be a positive. This times this, we'll switch them around, this becomes negative, and then we get that result. And this is the quotient of two complex numbers in polar form. So here we divide the one margin by the other, and notice that we have to subtract the argument of the second from the first. And that's how it's done. Complex numbers in polar form. And of course, first we need to put them into polar form because we're not given the two numbers in polar form. So first we need to find R for the first one. R1 is therefore equal to the square root of 1 squared plus 1 squared, which is equal to the square root of 2. Over here, R2 is equal to the square root of the square root of 3 squared plus 1 squared, which is equal to the square root of 4, which is equal to 2. And to find the angle, theta is equal to the arctangent of, well, that would be, let's see here, that would be b, that's minus 1 over 1, which is equal to negative 45 degrees, which is equal to negative pi over 2. Now, for the angle on this one, we can say that theta sub 2, and I should call this theta sub 1, is equal to the arctangent of b, which is 1 over the square root of 3. And let's see here, what is that equal to? I think 1 divided by square root of 3. Take the inverse tangent, yes, 30 degrees, that is equal to 30 degrees, which is equal to pi over 6. Alright, now we're ready to multiply both of them in polar form. Now we can say that G1 times G2, which is equal to R1 times R2 times the cosine of theta 1 plus theta 2 plus I times the sine of theta 1 plus theta 2. So let's go ahead and plug that in. This is equal to R1, which is the square root of 2, times R2, which is 2, times the cosine of theta 1 plus theta 2, which is a minus pi over 2 plus a pi over 6. Wait a minute. That's not pi over 2. This is pi over 4. Oh, I want to do that. Pi over 4. That's 45 degrees. Plus I times the sine of, again, that would be a minus pi over 4 plus pi over 6. Okay, now we need to simplify that, and that looks as follows. 2 times the square root of 2 times, well, we have a minus pi over 4 plus pi over 6, common denominator is 12, that's minus 3 plus 2, so this becomes the cosine of minus pi over 12, plus I times the sine of, again, this would be the same, that would be minus 3 plus 2, or minus pi over 12, and of course we can simplify that because the cosine of a negative angle changes the cosine of a positive angle, so this could be written as 2 times the square root of 2 times the cosine of pi over 12. And then we can transfer the negative over here, minus pi times the sine of 12. Like that, and that would be the end result of the product when it's in polar form. So notice the hardest part was probably converting it to polar form. Once it was in polar form, it's very easy to figure out the product of two complex numbers. Of course, don't make a mistake. That's not fun. And that's how it's done.